Good morning, students. This is Aravind, Assistant Professor, Department of DBSIT, KAVALI. In the previous class, I discussed about different characteristics of Svc&Statcom, and now in this class, we will discuss one more characteristic of this Svc&Statcom, that is VAR generation, that is a VAR optimal control, that is it is also called as operating control, operating point control. And next, we are going to discuss summary of compensator control. Okay, like that we are discussing in today's class. So first I will start with the last characteristics of Svc&Statcom, that is VAR reserve control or operating point control. Okay. VAR reserve control or operating point control. So in this one, as evident from previous classes, that is as evident from the previous sections, that means previous characteristics. Those are like the transient stability, polarization, damping, and we have a few more characteristics there. So, as evident from the previous sections, a static compensator has the functional capability to handle dynamic system conditions. Okay, a static compensator has the functional capability to handle dynamic system conditions, so such as transient stability and polarization damping, in addition to providing voltage regulation. So, in the previous class, I discussed about this transient stability enhancement and polarization damping concept. So, in that one, I use this voltage regulation. So, here, as evident from the previous section, so in the previous section, we discussed about the static compensator. So, based on those things, the static compensator has the functional capability to handle dynamic system conditions. Okay, so such as transient stability and polarization damping, in addition to providing voltage regulation. Okay, so next, so even in the area of voltage regulation, you know already voltage regulation. So voltage regulation is defined as the ratio of difference between no load voltage to full load voltage to full load voltage. Okay, so even in the area of voltage regulation, the static compensator is viewed primarily as a fast VAR source. Okay, viewed primarily as fast VAR source to counteract rapid and unexpected voltage disturbances due to faults, line and load switching, generator outages, etc. So, based on these faults, we have to take the action primarily as a fast VAR source to counteract these things, the unexpected voltage disturbances due to faults, line and load switching, and generator outages. Like that, we are facing so many problems. So, to overcome, so to counteract those things, we have to use this static compensator primarily. Okay, next, so in order to fulfill these application requirements, it is necessary to ensure that the compensator will have sufficient VAR capacity. So this is the main thing we have to think. That is, we have to handle we have to check the sufficient capacity of that VAR, what we are using, that is VAR reserve control or operating point. So we have to check the capacity of that one, okay, to handle unpredictable dynamic disturbances. So why we are checking that capacity of the VAR means VAR reserve control means, so if it has to handle the unpredictable dynamic disturbances or not. Okay, for that case, we are using this one. So that is in order to fulfill these application requirements. So it is necessary to ensure that the compensator will have sufficient VAR capacity. So the compensator will have sufficient VAR capacity to handle unpredictable dynamic disturbances. So this is often accomplished with an automatic control. Okay, this is also previously we discussed these things are often accomplished with an automatic control that maintains predetermined VAR reserve by adjusting the operating point of the compensator. That's why I am taking the VAR reserve or operating point control characteristic here. So this is often accomplished with an automatic control that maintains predetermined VAR reserve by adjusting the operating point of the compensator. So, the objective of this control is to limit the steady state reactive power output of the compensator, that too for a given reference value. So, that's why we are using this characteristic. That is where reserve control or operating point control. The main objective of this control is to limit the steady state reactive power output of the compensator to a given reference value. So the basic concept is to allow the compensator to change its output rapidly to counteract transient disturbances. So the basic concept of this control is to allow the compensator to change its output rapidly to counteract transient disturbances. Okay. So however, when a disturbance results in a new operating point, so actually we are operating on operating point, but however, when a disturbance results, so after the disturbance in a new operating point with a steady wear output, the wear reserve control effectively changes the voltage reference. So actually, I said that previously the objective of this control is to limit the steady state reactive power output of the compensator to a given reference value. But here, the wear reserve control effectively changes the voltage reference in order to bring back the wear output slowly to the set reference value. That's why we are using this control, this characteristic. Okay, and thereby activating slow wear sources. So actually, in the previous class I discussed about fast wear sources, but here if you want to bring down the bring back the wear output slowly to the set reference value and thereby activating slow wear sources, that means example mechanically switching capacitors and other compensating means to pick up the steady state wear load. So to pick up the steady state wear load, we have to use these slow wear sources. That means generator excitation like that we are taking, and by using those things, we have to pick up the steady state wear load. Okay. And next, so actually the response time of this control loop is slow, not to interfere with the rapid voltage regulation or any fast stabilizing or auxiliary functions that might be included in the overall wear output control. So actually, every compensator or every restriction of the response time, okay, or time constant. So here the response time of this control loop is slow. Why? Because in order not to interfere with the rapid voltage regulation or any stabilizing or auxiliary functions, while that might be included in the overall wear output control. That's why I am taking one possible scheme to implement a basic wear reserve control. Okay, a possible scheme to implement a basic wear reserve control is shown in the diagram, that is this one. So this is the implementation of wear reserve control. So actually this diagram is similar to the previous concept also. That is the previous concept, that is the characteristics of the previous ones, that is transient stability, power loss and damping. Previously we discussed about a few more. So all the things are included here. So it consists of one power system. So it consists of two generators. So one is consisting of voltage and another one is consisting of change in voltage, and these two are connected to the impedance. There is it is a function of angular frequency and time, and also it connects to the terminal voltage of providing the power system, that is V and delta V. So that is terminal voltage, we have to take Vt plus delta Vt of t, and then it is connected to static generator along with the voltage measuring and processing circuits, and this coupling transformer. So this one is connected to current measuring and processing circuits, and then it is given to the feedback, which consists of the reactive current IQ, and after giving this to the feedback, so it is converted into delta IQ, that is change in the reactive current, and this will given to the slow error integrator, and this will given to one more feedback. So it consists of V reference value, okay, and then it is given to the effective value of the reference, that is voltage value, that is V reference star, and it is given to the PI controller, and it is given to the output of this one is reactive current reference value. So that is given to the static generator. Like that we are taking this one. Okay. So by using this, so the magnitude of the output current of the compensator is measured and compared against the reference, that is IQ conjugate. So this is. So current measuring and processing circuit is comes to the feedback. So actually the current measuring and processing circuit gives the reactive current to this feedback, and it also takes the IQ conjugate value. So that is the magnitude of the output current of the compensator is measured and compared against the reference value, that is IQ conjugate. Next, it gives the error signal, that is delta IQ. So if you observe this one, it will use the delta IQ. This is the error signal, and it is given to the slow error integrator. So this error signal delta IQ is processed by an integrator of large time constant and added to a fixed voltage reference, that is V reference. So this one is given to the voltage reference. So reference value of the voltage in the system, that is V reference. So this delta IQ value is given to this one after integrating this one. Okay. So here I already said that. So is processed by an integrator of large time constant. Integrator of large time constant. That's why I am taking K into integral delta IQ into dt. So and then it is given to the V reference. Okay. Next, this forces, that is delta IQ and V reference value forces the input signal to the voltage regulator. So this forces the input signal to the voltage regulator to change until the difference between the actual output current of the compensator and the steady state output current reference, that is IQ conjugate, become equal. So so whenever the delta IQ is processed by an integrator of large time constant added to the fixed voltage reference, this forces the input signal to the voltage regulator to change until the difference between actual output current, that is IQ of the compensator, and steady state output current, that is IQ conjugate, both are equal, to become equal by this will use. Okay. And next, so the operation of simple wire reserve control described is illustrated in this figure. So it will give the diagrammatic illustration of the concept of wire reserve control. Okay. So that means, so here I am assuming the compensator is operating at I, that is in this one IQ is equal to IC1 on the VA curve. So if you observe this diagram, so here we have, so here I will draw the diagram between IC, that is current versus voltage. So that voltage is a terminal voltage and current is the inductor current and at the same time capacitor current. So here I am considering the midpoint. So midpoint I am drawing a horizontal vertical line, that is the VT line. And next we have two responses, one is slow and one is fast. Actually I am taking 3 points here, 1, 2, 3. Okay. So Svc&Statcom and that is, so here in this one assume that the compensator is operating at point I on the VA curve. When a disturbance in the form of sudden delta will drop in the amplitude of the terminal voltage vectors, what will happen is the voltage change, that is delta VT. So the voltage change, that is delta VT. Okay. So delta VT forces via a fast voltage regulating loop. That's why I am taking this one fast. Okay. So here the voltage changes delta VT forces via fast voltage regulating loop. Next, the output current to increase from steady state value, that is I conjugate Q to IC2, and the compensator assumes working 0.2 on the VA curve. Okay, the compensator assumes working at the 0.2. So that is fast acting. Okay. However, since IC2 is greater than IQ conjugate. Okay. So, however, since IC2 that is greater than IQ conjugate, so at that time what will happen is, so an error signal delta IQ is generated. So an error signal delta IQ is generated. That's why I am taking this one, this line. Okay. Instead of origin point, we have IQ conjugate. So this one. So however, since IC2 is greater than IQ conjugate, an error signal delta IQ is generated within the wire reserve control loop, which via the slow integrator. That's why it is working at the point 3, that is slow. Okay. Slow. That is the control loop. So which via the slow integrator, it changes the reference signal to the voltage regulator. So it changes the reference signal to the voltage regulator forcing the compensator to reduce slowly its output current, So the compensator finally assumes a new steady state in working point 3 on the VA curve. Okay, the compensator finally assumes a new steady state in working point 3 on the VA curve. That's why I am taking this 3 point. Okay. Next, the structure of static compensator control illustrating the underlying principle of superimposing auxiliary input signals on the basic voltage reference to carry out specific compensation functions automatically as required by system conditions, that is shown in this diagram. So this is the diagram. It will give the structure of the basic compensator control for multifunctional power system compensation. So that's why I am taking damping, over voltage limitations, static wave generator, and we have V/IQ drop character and wear reserve, and transient stability enhancement, power reduction damping, like that. Okay, so in this concept, I am taking the summary of compensator control. So up to now we discussed about wear reserve control, that is the last characteristic of the Svc&Statcom, and now we are moving to the next concept, that is summary of compensator control. So in this one, the structure of static compensator control, okay, the structure of static compensator control is illustrating the underlying principle of superimposing auxiliary input signals on the basic voltage reference, to carry out specific compensation functions automatically as required by system conditions, that is already shown in this diagram. So here we consist of all the characteristics, not only one. Here we are considering all the characteristics, that is V/IQ drop character, wear reserve control, transient stability enhancement, power reduction damping, like that we are taking, and we are having the static wave generator, that is the main thing, and we are having the power system connection. So in this one we are considering one generator distinction to the prime mover. In the other we have the frequency that and which is omega m plus delta omega m of t. So and this one is given to the impedance that is Z. So Z of omega gamma t, and this one is given to the terminal voltages Vt plus delta Vt of t and Ft plus delta Ft of t, that is change in voltage and frequency with respect to time. And next we have this is connected to the static wave generator, and it is also connected to the voltage measuring and process circuits. In the other, this voltage measuring and process circuit is given to the effective voltage reference signal, that is V reference conjugate, and this is given to the PA controller, and this is given to the static wave generator. And in between PA controller and static wave generator we have one summation. So this summation is given to the over voltage limitation and SSR damping. And after that we are taking an auxiliary input and a reference signal V reference, and it is connected to summation, and it also connected to the all the four characteristics of this one, that is V/IQ, that is voltage current characteristics and voltage reactive current characteristics, like that, and VAR reserve control and transient stability enhancement and power reduction damping. Those are connected to this one. Okay. And after that it is given to the effective reference signal, that is V reference. Okay, like that we are taking. So with this principle, the compensator within its MVA rating and operating frequency band acts as a perfect amplifier, forcing the magnitude of the regulated terminal voltage to follow the effective voltage reference, which is the sum of the fixed voltage magnitude reference and auxiliary signals. Okay. So with this principle, I am taking the compensator within its MVA rating and operating frequency band. Okay, that time it will act as a perfect amplifier. So this is forcing the magnitude of the regulated terminal voltage to follow the effective voltage reference, that is V reference conjugate. So which is the sum of the fixed voltage magnitude and reference auxiliary inputs. So this one auxiliary inputs and reference signal. So auxiliary input and V reference is given to summation, and it is given to the effective reference signal, that is V conjugate reference, like that, and it is last with the static wave generator. Okay, so apart from the real time control functions, okay, apart from the real time control functions, I will show another diagram. So this diagram, okay, this diagram explains the total control system of a modern static compensator has many other elements to manage the proper and safe operation of the equipment with high reliability and availability. Okay, the total control system of modern static compensator has many other elements to manage the proper and safe operation of the equipment with a high reliability and availability, as well as to accommodate proper interface with local and remote operators, as shown in the glossary manner in this diagram. So this one. So here I am taking the main elements of the complete control operating a static compensator. This is the complete control system we are using for the static compensator control. So in this one we have bus bar and coupling transformer and SVG, static bar generator, power circuit, and interface we have, and we have optical links, and it will give to the interface, and we have SVG internal control. Okay, we have SVG power circuit and SVG internal control, and we have compensator internal control, and we have supervisory control and status monitor, and we have control panel and CRT monitor, and measured system variables we have. Sorry. So we have auxiliary equipment and system status input, and we have SCADA. Like that we are providing in these main elements of the complete control operating a static compensator. Okay, so this will give the total control system of a modern static compensator has many other elements. Why? Because to manage the proper and safe operation of the equipment with a high reliability and availability, as well as to accommodate proper interface with local and remote operators. Okay, that's why I am taking this interface and optical links. And next, so the main elements of this overall compensator control system include first one, that is interface between high power, high voltage semiconductor valves of the overall switching converter and PSC and the TCR structure, and a highly sophisticated real-time control required for the internal operation of the DAC generator and for the result system compensation functions. We have interface between high power and high voltage semiconductor valves. So this is, we have interface between this one, that is SVG internal control and compensator internal control. That's why I mentioned this is the first main element, that is interface between high power, high voltage semiconductor valves of the overall switching converter, that is PSC and TCR structure, and a highly sophisticated real-time control required for the internal operation of the DAC generator and for the desired system compensation function. And so this interface transmitting gating commands from the control to the valve. Okay, so whatever the interface we are using, the transmitting gating commands from the control to the valves, okay, and status information from the valves to the control is usually implemented by optical links. So in this diagram we are providing optical links between interface and SVG internal control. So this is used to transmitting gating commands from control to the valve, and status information from the valve to the control is usually implemented with optical links. That's why I am taking either direction. Both directions I am taking in the diagram. Okay. Next, second one is signal measuring and processing circuits and equipment variables. So system signal measuring and processing circuits. So this one, system measuring and processing circuits and system variables we are using, that is in the top of the diagram. Okay. So signal measuring and processing circuits for the system and equipment variables. So in this one, the real-time control and production relays need as input. So in this one, the real-time control and production relays, that is operator displays. So need as input certain system variables, okay, such as terminal voltage and compensator output current, as well as appropriate internal voltages and currents of the equipment, from which magnitude, phase frequency and other relevant information can be derived to follow in real-time construction, in real-time system conditions, and monitor equipment operation. Okay, the real-time control and production relays need as input certain system variables, like we have terminal voltage, frequency, and compensator output current, that is IQ, as well as appropriate internal voltages and currents of the equipment, from which magnitude and phase frequency and other relevant information can be derived to follow in real-time system conditions and monitor equipment operation. That's why we are taking these things. And third one is supervisory control. Okay, we are having supervisory control. So this one. So the real-time control is given to supervisory control and status monitor. So this is the third one we are using. So supervisory control and status monitor, which interfaces with the all parts of the compensator. Okay, including all essential components of the compensator, proper and its support equipment, that is cooling system, power supplies, breakers, switches, interlocks, etc. All the equipment, all the components are including here in this one. Okay, and next, so after interpreting this one, so it collects status information from every part of the system. Okay, so it collects status information from every part of the system, usually via serial communication links, organizes and interprets the status data to determine the operational integrity of the compensator and to provide diagnostics of possible malfunctions and failures. So diagnostics means analysis to provide analysis for the possible malfunctions and failures, that means faults. So and it also carries out the startup and shutdown sequencing and other operating routines of the compensator and provides appropriate communication links for the local and remote operators. Okay, that's why we are using the supervisor. Okay, the status information control, and we have fourth one, that is user interface with CRT graphical display. So in the diagram we have connection to supervisory control status mode is connected to the control panel and CRT monitor. So in this one, so user interface with CRT graphical display is usually provided by a standalone computer with an appropriate CRT monitor and keyboard and pointing device, that is mouse for data entry. Okay, this computer usually has a serial link to the status processor and runs in graphical display and control software. Okay, so through the interface, a large amount of information is available for the operation. Through the total interface, we have a large amount of information is available for the operation and diagnostic and maintenance purposes in graphical and numerical form. Okay, so the information includes, so what is the information we have to take means, so that is status information from the valves, identifying failed power semiconductors and other components and associated circuits, and selecting operating modes of the compensator and associated control and operational parameter settings, and control operating and redundancy, and status of support equipment such as cooling system, actuator, power supplies, breakers, switches, etc. Already we discussed about these things. And building climate status, that is temperature, humidity, etc. These all information is given by the total interface. Okay, in the graphical and numerical form. Okay, so this is the summary of static track control. Okay, static track control, compensator control. So after that we discussed about characteristics of Svc&Statcom and summary of static compensator control. And we are moving to the next concept, that is comparison between Statcom and STC. So comparison between Statcom and STC. So after now we discussed so many concepts. So in this one, I am going to discuss the comparison between Statcom and STC. So on the basis of explanations provided in the previous section, that means Svc&Statcom characteristics we discussed up to now. So based on those explanations, so it should be clear to reader that on the one hand, in the linear operating range, the VA characteristic and functional compensation capability of the Statcom and STC are similar. So VA characteristics and functional compensation capability of both Statcom and STC is similar. Okay, next, however, the basic operating principles of the Statcom, which with a converter-based valve generator functions as a shunt-connected synchronous voltage source and fundamentally different from those of the STC. So that means the operating principles of the Statcom and STC is different. So in the STC we are using thyristor control reactors, but in the Statcom we are using converter-based valve generator, and in the STC we are using thyristor switching capacitors also. That is the TSC, TCR, and functions as a shunt-connected controlled reactor admittance, but in the Statcom it functions as a shunt connected synchronous voltage source. Okay, so like that we are differentiate those things, SHUNT, and the basic operational difference, that is voltage source versus reactive impedance, accounts for the STATCOM's overall superior functional characteristics, that is better performance and greater application flexibility than those attainable with the SVC. That is, there is a basic operating difference between SVC and STATCOM also. So these operational and performance characteristics are summarized here with the underlying physical reasons behind them and with the corresponding application benefits. So from the next slide also, I am going to explain the comparison between those all performance characteristics like VA characteristics, VQ characteristics, between SHUNT and response time and physical size and ratings and exchange of real power, like that we are discussing. We are going to discuss. So these are the different comparisons between STATCOM and SVC. Those are VA and VQ characteristics, that is voltage current and voltage reactive power characteristics, and transient stability and response time and capability to exchange real power and operation with unbalanced AC system and loss versus wear output characteristics and physical size and installation. These are the various performance characteristics we are using to compare the STATCOM and SVC. Firstly, I am taking VA and VQ characteristics. So in this class, I am going to discuss this VA and VQ characteristics, and in the next classes, I am going to discuss these remaining characteristics. Okay, comparisons between SVC and STATCOM. So firstly, I am taking VI and VQ characteristics. So actually, the STATCOM is essentially an alternating voltage source. You already know this one. The STATCOM is essentially an alternating voltage source behind a coupling reactance with the corresponding VI and VQ characteristics, that is voltage current and voltage reactive power characteristics, that is shown in these diagrams. Okay, these two diagrams gives the VI characteristics of the STATCOM and VQ characteristics of the STATCOM. Okay, so in this one, these show that the STATCOM can be operated over its full output current range even at very low, typically about 0.2 per unit system voltage levels, by using these two diagrams. So if you observe this one, I am taking the curve between interaction diagram between voltage and current. So voltage means here I am taking terminal voltage, and current means I am taking both inductor current and capacitor current. So in this one we have transient rating, that is t less than 1 second, and transient rating is 1. So in this one I am taking voltage in per unit, that is 0 to 1 per unit, that is 0.2, 0.2, 0.3, like it up to 1 per unit I am taking. So in this one I am taking the maximum current limit of the capacitor and inductor, that is IC maximum and IL maximum, at 0.9. Okay, so the curve is like this. Okay, for every point I am drawing one cross line and combining the points from 0 to 1 in this manner. And in the STATCOM I am taking the graph between voltage and reactive power. Okay, so that is, in this one I am taking voltage as our terminal voltage, and next I am taking inductor and capacitor powers, and maximum current at capacitor, maximum current at inductor I am also taking. Here also I am taking the voltage ratings as 0 to 1 per unit. Okay, so here, so these show that the STATCOM can be operated over its full output current range even at very low, that is theoretically 0, typically about 0.2 per unit system voltage level. So in other words, the maximum capacitive or inductive output current of the STATCOM can be maintained independently of the AC system voltage, and maximum wear generation or absorption changes linearly with the AC system voltage. So like that, the maximum capacitor inductive output current of the STATCOM can be maintained by using the independent AC system voltage, and also maximum wear generation or absorption changes linearly with the AC system voltage. And next, so in contrast to the STATCOM, first now we discussed about the STATCOM, and next we are moving to the SVC. So in contrast to the STATCOM, the SVC being composed of 5 substitute capacitors and reactors. You know already this one. The SVC consists of PSC and TCS like that. So it becomes a fixed capacitor which is at full output. Okay, this becomes a fixed capacitor which is at full output. So thus the maximum attainable compensating current of the SVC decreases linearly to the AC system voltage, and maximum wear output decreases with the square of this voltage as shown in these diagrams. That is two diagrams I will show. So these two gives the SVC characteristics of the VA and VQ. So that is VA characteristics and voltage characteristics of the SVC, and VQ characteristics of the SVC. So in the previous two diagrams I explained about VA characteristics of the STATCOM and the VQ characteristics of the STATCOM. And now in this class I am going to discuss SVC and SVC characteristics, VA and VQ characteristics of the SVC. So from those diagrams, so if you want to get the maximum compensating current of the SVC, actually it decreases linearly with the AC system voltage. Okay, it decreases linearly with the AC system voltage, and the maximum wear output decreases when with the square of this voltage. So this one. So it is linearly decreasing. Okay, in this one it is linearly increasing like that. So here the STATCOM is therefore superior to the SVC in providing voltage support under large system disturbances, during which the voltage excursions would be well outside of the linear operating range of the compensator. Linear operating range of the compensator. So that means a STATCOM superior to the SVC. Okay. Why? Because in that one we are using the voltage source. Okay. Next, the capability of providing maximum compensating current at reduced system voltage enables the STATCOM to perform in a variety of applications the same dynamic compensation as an SVC of considerably higher rating. Okay, the capability of providing maximum compensating current at reduced system voltage enables the STATCOM to perform in a variety of applications the same dynamic compensation as a SVC of considerably higher rating. So here I will show the diagrams. So these things SVC. Okay, each the STATCOM depending on the power semiconductors used have an increased traction ratings in both the inductor and capacitor operating regions. Okay, then the maximum attainable transient over current of the STATCOM in the capacitor region is determined by maximum current runoff capability of the power semiconductor. The example is GTO thyristors. So we have to apply these GTO thyristors. It is determine the maximum current runoff capability in capacitor region. Okay. And next, so moving to the inductive operating region, the power semiconductors of an elementary converter switched at the fundamental frequency are naturally commutated. Okay, in the inductive operating region. So actually we have two regions. One is inductive region and another one is capacitive region. So in the inductive operating region, the power semiconductor of an elementary converter switched at the fundamental frequency are naturally commutated. So this means that the transient current rating of the STATCOM and the inductive range is theoretically limited only by the maximum possible GTO junction temperature. So which would in principle allow the realization of higher transient rating in the range than that attainable in the capacitive range. So however, it should be pointed out that this possibility would generally not exist if the converter poles were operated to produce a pulse width modulated waveform when the current conduction between the upper and lower valves is transferred several times during each fundamental half cycle. Okay. And next, even with non-PWM converters, abnormal operating conditions should be carefully considered in the implementation of transient ratings above the peak turn-off current capability of the semiconductors employed. Okay, up to now we discussed about PWM converters, and even with the non-PWM converters, the abnormal operating conditions should be carefully considered in the implementation of transient ratings above the peak turn-off current capability of the semiconductors employed, because if an expected natural combination would be missed for any reason. That's why we are taking non-PWM converters. So the reason that this converter failure requiring a forced shutdown would likely occur. Okay, so that's all for today. And in the next class, I'm going to discuss remaining comparisons between SHUNT and STATCom. Okay, thank you for watching this video.